Live, rocking and rolling. Who did anything cool in the lab last week? One hand? Nobody? You guys don't like the labs? Who took the class primarily because of the labs? Be proud. Be proud. Who took the class primarily because of the labs? But you came to the lecture anyway? Well, even Charlie raised his hand. Took the class primarily because of the labs. Why? Guy that's next to Charlie. Why? Ooh, you're on camera. To see if you like manufacturing. Okay. So and certainly using the CNC machines and stuff helps you learn something about manufacturing, right? Is that true? I think I've assembled my tripod poorly. Oh, got it. Spin this part around. Yeah, it's not going to go all the way around. Spin this part that way. Now I can put it here. Go like this. And now people watching at home on YouTube can see the blackboard with nothing on it. All right, so you want to learn something about manufacturing. Who else wants to learn something about manufacturing? See if you, somebody said, see if I like manufacturing, right? That's what you said? Who else wants to see if they like manufacturing? Hale. Yes. If I put my glasses on, I can read your name tags better. What made you think you might want to learn about manufacturing? Like hands-on work. Cool. That's it? Okay. Anybody else? What made you think you wanted to learn something about manufacturing? Anybody? Had any reason? Who wanted to learn something about manufacturing? Put your hands back up. So I forget your name. Josh. Why did you think? Butter's cool. Butter does make everything better, except for possibly bacon. Bacon and butter are sort of up on pedestals. I don't know. What are we going to learn about today? I said it just a minute ago. Who's listening? Yes. We're talking about energy and power today. What is energy? Okay. Well, I have it on the counter. It's on something. Is that better? Thank you. Give him a bonus point. Okay. Oh, so this video is actually kind of cool here. I made this video almost for this. Oh, wait. I made this video for this lecture in A-term. Let's play this video again. Have we played this one before? Have you guys seen this one? No. Okay. There's some volume. This is not the classroom that freaks out when there's volume, right? So yeah, I'll even let the people watching on YouTube see what's going on. All right, people watching on YouTube, you can see what's going on here too. All right, let's play the thing. Whoa, it's kind of got volume, right? You guys can hear the spindle? Okay. So when it did that, we went across here. So you see there's this spindle load meter here, right? You guys notice that when you were operating the machine tools? I think on the newer controllers, on the VM2 and the Super Mini Mill, it's actually just a graphical display on the controller. On the older machines, it's actually a gauge. The needle moves up and down. So where's that needle sitting right now? Right, it's about, so this mark right here is 50%. So it's about halfway between 0 and 50%, so about 25%. And what they do here, actually, this meter goes up to I think these go up to 200, maybe 185. So why does the meter go to 200%? Just let's get that out of the. Why would the meter go to 200%? Yes. Robert, right? Yeah, I got one. Yeah, so there's a range in which it's okay to operate that spindle in a speed, right? And so, because these are servo motors with servo motor controllers and stuff like that. And so when it's at 100% power here, that's sort of where it wants to be all the time. And it can go up to like 150% as long as it's doing this throughout the day. And you're not going to break anything. When you start getting past 150%, you get to like 180, 190, you're at risk of damaging components or making them wear prematurely. And so that's why they'll let that spindle go up. Oh, on the other hand, it's like marketing too, right? Turn the volume up to 11. Turn the power up to 200. Okay, so that's why they do that. But so we're at 25% power here. Let's see what happens on the next pass. So what's the first thing you noticed as the tool engaged? Yeah. So the needle went further up. And so what's it at? It's at like 75 or something, maybe getting close to 100% now. Did you notice anything else between the first pass and the second pass? Yeah, Charlie. It sounded different, right? Yeah. Say again. Okay, yeah, it fluctuates a little bit. Right now, it's sitting there close to 100%. But Charlie noticed it sounded different. Was it a higher frequency or a lower frequency? It was certainly louder, right? I think the frequency was a little bit lower, but maybe about the same, but certainly louder. All right, so let's finish this pass. So what do we notice here besides that it's up at 180%? Yeah. Yeah, actually, before the tool engaged the material, you got one sound. As the tool starts to engage the material, you could hear the spindle slow down. Right, that's the sound of the spindle slowing down. If you're running the machine tool and you hear the spindle slow down, what should you do? You could e-stop, right? You could stop the feed. What's going to happen if you stop the feed in this situation, at least? It'll stop moving into the workpiece material, right? And the spindle will speed back up. You could do that. If I knew it only had a short distance left to go, I might just do nothing except look at it. It's actually a thing where you add weights to the tool holder. Why would I want to add weights to the tool holder? Make the tool holder heavier than it was. Or you just use a heavier tool holder. Yeah, why? So it has more inertia, right? More momentum. And you call this, and when you're using that principle in order to get through the cut, we'll call that inertial milling. That's when we're using, so what causes, so the spindle load goes up. What's load? What's another term for load? Yeah. Resistance, okay. All right, that's enough of that. Let's get this thing turned on. Display sources, document camera, this one. Okay, and on the computer, let's get our agenda up so we can stay on track because we're already behind track. Okay. Engineering's math. Just a bunch of word problems. Cancel the units. So, first off, that's a poem, right? You guys know that's a poem? What kind of poem is it? It's a haiku. Now, it's not the traditional haiku, because the traditional haiku would be Japanese, and it would be about nature. I suppose engineering, nature is made up of engineering, sort of. All the stuff we see around us is naturally there because of engineers. All right, so keep that in mind. What's it take to make a haiku, Charlie? Syllable count. 5, 17 syllables, right? To make a haiku. If you want to write a haiku, what do you need? 17 syllables is what you need if you want to write a haiku, right? Okay. If you want to write a good haiku, what do you need, Mustafa? If you want to write a good haiku, what do you need? Yeah. Inspiration. I would say you need the most important 17 syllables about the thing your haiku is about. And so I use haiku in order to focus my mind on the thing I'm talking about. And so engineering's math, just a bunch of word problems, cancel the units. So what's the hardest thing to do when you're doing a word problem? Yeah. Understand the problem, right? That I paraphrase. Hardest thing to do if we're doing a word problem is to understand the problem. So if we're going to talk about energy, power, work, we're going to talk about estimating power in our CNC machines. We're going to talk about the machinery's handbook. What's energy? What's energy? Yeah. Energy equals what? V squared what? Let's get more basic. You're giving me an equation for what's energy. If we got to cancel the units, what are the units for energy? You guys know the units for energy, right? Yeah. Joules. Units for energy are joules. What's a joule? What's a joule? Yep. Equals Newton. Newton what? What is it again? I didn't hear. Yep.
It's meters, meters times, meter squared times mass divided by second squared.
Meter squared times. So what's units for mass if we're using meters, kilograms? Meter squared times mass divided by second squared. Is that the units for energy? Joules. Meter squared times mass divided by second squared. Yeah. Is it Newton? A Newton is what? Say it again. Yep. Newton is a kilogram meter per second squared. And then times a meter equals a joule. Right? So you thought it right. Newton meters. Okay. That's energy. Now, what is energy though? What does it mean? So now we've got units for energy. What is energy? Yes. It's potential to do work or ability What's work? Yep. Use of energy. Okay. What are the units for work? So if we're sticking to our metric unit system here, what's force? What's distance? So the units for work and the units for energy are the same. Whoa. So what does that mean? Yeah. Work and energy are the same, except for energy is that potential to do work. Work is the result of applying the energy. Now, what's power? Yep. So power is work over time. That's how we do rate, right? Power is the rate at which work is done. So units then is watts. Watt is a watt. What is a watt? Yep. Newton meter per second. I'm going to pull this one back down. A watt equals a Newton meter per second. Hey, what's a Newton again? Kilogram meters per second squared. So let's see. Kilogram. If I've got my. Here's a clean space on the whiteboard. If I've got my kilogram meters per second squared, and I divide that, right? A watt is a Newton meter per second. I divide that by a second. What does that give me? It's up here. Kilogram meters per second squared divided by second. Did I have everything here? Do I need meters here? Where do the meters get squared? Top one. Yeah, or I just write it there. I can square it. Now it's right. What's it equal? Is it no? I think so, right? All right, so this is times. You're right. Is that right now? Okay. Does it also equal this? Kilograms meters per second squared times meters per second. And what's that equal? So this is newtons, right? Did we get back to newtons? Is this force? Is this velocity? Power equal force times velocity? All right, let's think of our machining exercise then. If power equals force times velocity, in our machining exercise, if we're, so when we're doing our machining, let's take a turning. If we were turning on the lathe, so we've got our cutting tool here. We've got our chip forming on the edge of the cutting tool right there and sliding off. We've got a diameter. We've got an original diameter out here. We've got a finished diameter out here. The way we get that finished diameter is by moving the cutting tool in this direction, right? What do we call that when we move the cutting tool in this direction? That's the axial feed or just the feed rate, the feed. Now, what is the velocity that's going to, so it takes energy. You have to do work on the workpiece material in order to get that chip to form. We have to. And we can know what that power consumption was. We can know what the power was if we know the force and the velocity. What's the velocity?
Isn't it the surface speed when
It's the surface speed at the cutting edge, right? So it comes from the rotation. So all of the velocity that we're considering when we estimate or when we calculate the power for our machining operation comes from the rotation of the spindle. The feed, what does the feed give us? So what does that feed give us? It gives us a new place at which to apply the power, right? If we don't have the spindle spinning and we just drive the tool into the workpiece, can we cut? Maybe. We call that a broaching operation. Maybe we can cut. And then in that case, the velocity comes from the feed. But what's the surface speed for a, I don't know, this is about 2 inches at the cutting diameter. What's the surface speed for 2-inch diameter part at, call it 1,000 RPM? Anybody get a calculator? Quickly do it. 2-inch diameter times pi, right? Pi times diameter times RPM. And then we either multiply or divide by 12 to turn it into feet. Yep. Times 1,000. 2 inches.
but that's per second, not per minute.
Oh, per second. So what do we got per minute? 523? Is that correct? Okay. Anybody know in a turning operation what the typical feed rate is? Could be anywhere from, I don't know, 1 to 6 inches a minute, something like that on a part like this. It's all right, 0.003 times, so that's inches per revolution, times our RPM, 0.03 times 1,000. So 3. Hey, I picked 1,000 RPM to make the math easy, and then I forgot. So 3 is what percent of 500? Ish.
About 1%.
About 1%, a little bit less than that. Yeah. All right. A little more? Okay. So the impact of the feed, so because it's not just the spinning, right? It's also feeding in this direction. It's moving in 2 directions through the workpiece material. So the impact of that feed, we could say it's negligible compared to the impact of the rotation, unless you stop the rotation, in which case all the cutting happens from the feed. Okay, so power equals force times velocity, and it happens at the edge of the cutting tool. Now, the spindle meter that we were looking at was not measuring the power at the edge of the cutting tool. What was that measuring?
Load.
It was measuring what load? It was no. It's really hard to measure, to directly measure the power at the tool chip interface. Do you believe that? Because you'd have to be at the tool chip interface with your sensor to directly measure that power. What you can do, though, is you can measure the power that goes to the spindle through the power lines. And I think that's what you were trying to say, right? So we measure the power that goes to the spindle through the power lines. How much of that power gets to the chip? 100%? 200%? It's going to be less than 200%, right? It's going to be less than 100%. There's some efficiency factor, right? Because the bearings in the spindle will rob some energy. Some of it goes into heat, right, inside the machine tool. Some of it's electrical resistance inside the control unit. Okay, so not all of it gets there. But if we wanted to estimate, so, all right, we know power equals force times velocity. How do we measure the force? Could we measure the force directly? If you had to measure the force, if all you needed to do to graduate from WPI was figure out how to measure the force in this cutting, could you figure it out? If all you had to, yeah, Hale, what? You can, if, the question was, does it measure it through the spindle as well? And what I'm trying to do is, we know the velocity. How do we know the velocity? Yeah.
We know the RPM.
We picked it, right? We picked the velocity. If we can measure the force, then we can know what the power is. Okay? If we wanted to measure the force, so yes, if we measure the power, we can figure out what the force is if we know the velocity. So I think that's what you're answering. But if I wanted to measure the force and calculate the power, how do I do it? If all you had to do is figure this out in order to graduate from WPI, what would be your first step in figuring it out? You could, but it wouldn't work.
You know the materials, so you could.
Maybe it would work. You know the materials, yeah. We could estimate how much power we think it should take. That's the next step. But if I wanted to measure the power, measure the force. I just want to measure the force. How do you measure force? Who stepped on a scale today? Or yesterday? Who weighed themselves? Not me, I don't want to know. But, so how does the scale tell you how heavy you are? Yes?
Spring, and then the amount of compression.
So it could be a spring scale, right? You step on it, and a little needle goes up, and it's calibrated, and they calibrate it because they know what? What do they know about the spring? They know the K factor for the spring, right? So you can calibrate that. You can do it digitally with a different type of force sensor, an electronic force sensor. These little piezo stacks, you push on them, a voltage comes out, you can know how much force was applied. So you can actually get a force sensor, build it into the tool holder, or build it into the thing that holds the tool holder, and you can measure those forces directly. So it is totally possible to measure the forces. All right, so we measure the forces, we can get the power. Now, who was it that wanted to estimate the power? I forget, somebody said it. You wanted to estimate the power. If we want to estimate the power, And why might we want to estimate the power before we put the stuff in the machine tool? Yeah.
Get a rough idea if the machine will.
To get a rough idea if it's possible, right? Impossible. Yeah, I guess there's impossibles here. I don't like the word impossible. Improbable. But to get a rough idea if it's possible. Now, if we had to measure or estimate the power, what do we got to put into it? What do we need to know? What's going to impact how much power it takes to make this chip? Somebody in that quarter of the room. Somebody in that quarter of the room. Yes, Anna. So it depends on how big the chip is. Okay. So if we're going to estimate power, power is going to depend on the chip size. Now, how do we measure the chip size? What goes into the size of the chip?
How deep we cut.
How deep we cut. So our depth of cut is going to impact it, right? Yeah.
Material properties, how much it will, like how big of it you can get before it.
So that's a different factor. So there is a material factor. And so maybe we'll call it specific energy for cutting. There's a material factor. But the size of the chip is going to impact that. And it's easier because this is a continuous process. Instead of just thinking, so how do we measure size of something like a chip? Yes. You could measure the mass of the chip, but it's not going to help us that much right now. How else could we do it? Yeah. So the length is going to be a component. What else? The thickness and the width, right? So the size of the chip we can measure in volume, except this is a process that's flowing along, right? So instead of just the volume of one chip, how about we do the volumetric flow rate? Or the material removal rate. And this is in units of, if we're going to inches, it'd be inches cubed. So length cubed is our material removal rate. Length cubed, sorry, per time. So length cubed per time is our units for material removal rate. So how much material we're removing and the speed at which we're removing it is going to impact our power. The material itself is going to impact our power. What else do you think goes in to the power that it takes to make that chip? Yeah. Yeah. So the tool sharpness So the shape of the tool as it engages with the workpiece. So you call it sharpness, you can call it dullness. Is there anything else? Yeah. So how fast you want the part is actually included in our material removal rate. So yeah, that's a factor. So if we decrease the material removal rate, then it's going to take us longer to get the parts. So that's in there. So that was fun. I was working my home office the other day, and my daughter was watching some stupid. Do you guys who watches other people play video games? Do you also play the video game?
Yeah.
Okay, so my daughter does not. She just likes to watch people play Minecraft. She doesn't play Minecraft. She just watches people play Minecraft. And there was this stupid thing that there was a police siren in the game that they were videoing. And I kept hearing this police siren, and I kept looking outside to figure out is like all the cops on my street today? And no, it was because of the TV. Yeah. Anyway, so it turns out there's one more thing that we got to consider, and so this material factor here, right? So does it take more energy to cut aluminum or stainless steel? Raise your hand if you think it's stainless steel. Raise your hand if you think it's aluminum. All right, so democracy wins. Stainless steel takes more energy. Does it take more energy to cut brass or aluminum? I don't know. They're about the same probably. But there's tables of these material factors. How did they create the table? Yes. They did an experiment to create the table, right? And when they did the experiment, if you had to do the experiment, what would you do? Yeah. All right, so you gotta have some method to measure the power, right? And so we could measure it, we could look at the gauge on our thing. You can get more precise methods to measure the power going to the spindle. Okay, what else would you do? So that's the first step. Who's done an experiment before? Who's done an experiment before? Everybody has, right? You all graduated from high school and had a class where you did experiments. What else are you gonna do? Tiffany, we got our method for measuring power. Now what am I gonna do to set up my experiment? Use the same cutting tool for everything. That's a good plan, at least as we get started. So we get some dependent variables and some independent variables, right? How many independent variables do we want to have in our first test? We want to have one independent variable, right? So if we're trying to figure out material factors, what should the independent variable be? Yep. The material. It will keep our feed speed, depth of cut the same. We'll keep the tool the same. We'll do a bunch of different materials. Now, is that enough to really know? Right. So then we'll take a couple of those materials and we'll vary the feed speed, depth of cut, right? And see if it still works, right? We can do that. And so when they did that experiment, they found that they also needed what do scientists love to do when the answers don't come out right? So we have a theory, right? And we know that these things multiplied by each other are going to equal power, but they don't. They're close to power, but not quite. What do? You said it. We come up with a fudge factor. Let's call it C in this case. So we come up with our fudge factor, and it turns out that not only did they come up with a fudge factor, they figured out that that fudge factor was related to the feed rate. So material removal rate is related to the feed rate, and C is related to the feed rate. They determined that. If you want to know all this stuff without having to do the experiment, what should you do? Google is a good first start. Turns out I'll give you more specific instructions. You could use the Machinery's Handbook. If you happen to have my copy of the Machinery's Handbook, you could probably flip to this page that's got the green thing sticking out. Oh, that's totally not the right page. But if you have my copy, you could go to page 1054. And come on, 1054. Go to page 1054, where the section, is that focused? The section on estimating machining power starts on that page in the 28th edition. Now, what are you guys going to do to get the Machinery's Handbook? You could do that. You could get it from Amazon, or I don't know if they sell it on Amazon, but you could buy it online. You could buy it for like 150 bucks. Do you want to do that for this week's homework? No, good. I don't want you to either. So I will show you how to look it up online. Let's see, local PC, document camera. No, the other one. Is it up there? Okay, it's a very complex process. In fact, if you Google, find the Machinery's Handbook at WPI, you'll see a YouTube video of me showing you how to do this. But I'll make it so you don't have to watch the YouTube. You can Gordon Library. WPI library works too. You can click on the link for the library. You can click on this one here. It's a machine and I am demonstrating that you don't even have to spell it right. All right, maybe you have to spell it right. That used to work. Oh, there you go. Oh, you can get the 28th edition here. Available online. You get the 27th edition. You can get, I think you can get the 30th edition if you keep looking for it. But if you go here, 28th edition, available online. Not much in the way of estimating power has changed between the, I don't know, the 15th edition and the 30th edition. You can go here, click on your Novell. Okay, come on down here. You will have to sort through these unless you happen to know manufacturing processes, machining operations, feed speed tables, estimating speeds and power, and you can go right to that. If you are off campus, you can still do this. Start at the Gordon Library website. Go through the search. At some point, it'll ask you to type in your username and password, and then you'll be through the VPN or something. I don't know. They get something special set up, so you can access this. There'll be stuff that you'll need to look up in there to do the homework. Tomorrow, we're going to talk about the physics of that chip form. Tomorrow we're going to talk about the physics of the chip forming on the edge of the tool here, how this process happens, and how we can better understand our machining process if we understand that physics of that chip forming on the edge of the tool. And tomorrow I will talk about the first group project. So remember I told you there was going to be group projects and we were going to form groups? Did I have you guys form groups already? Start thinking about forming a group of 3 people. If you can identify your 3 people, identify them. Start thinking about forming a group of 3 people. And we'll get that set up as part of the first group project is to establish the groups and make sure that you're online and that you can get graded for doing the group projects. Okay? All right, so tomorrow we meet in Washburn 229, right? Not this classroom, Washburn 229 tomorrow. We'll continue the discussion of chip formation, energy, and power.